Hi, I'm Liam Farrelly. I'm a product engineer at Evervault, and today I'm going to be talking about Attestation for hosted workloads. Before I get started, I'd just like to thank Edgeless Systems for organising OC3. We've been huge fans for the last couple of years here at Evervault, so it's an honour to be involved. So, our agenda for today, we'll talk a little bit about Evervault, who we are, what we do, and how we use enclaves internally. We'll discuss the trust model for our latest product, Evervault Enclaves, which is an enclaves as a service model. And then we will do a walkthrough of the startup flow that Enclaves has, which uses Attestation to authorize the instances. After that, we'll have Q&A. So some context. At Evervault, we build infrastructure products to solve complex security and compliance challenges for our customers. All of these products deploy cryptography as the kind of central pillar for its solution. When we were building the initial infrastructure for our products, we needed a secure way to manage our users' private keys, and we did this using AWS Nitro Enclaves. So back in 2020, we became design partners for Nitro Enclaves and built the kind of foundational layer of our infrastructure on it, which we refer to as the Evervault encryption engine. So our experience building on Enclaves has been overall really positive. We were a small team when we first adopted it, and we found that Nitro Enclaves was a great solution to allow us to move quickly and deploy a small, tightly scoped service for managing keys. It did involve some heavy lifting to get to production, mainly around tooling, observability, and scaling. So for tooling, we had to rework our CI pipelines to support Enclaves as a deployment target. Up to this point, we also wrote most of our services in Node.js, which didn't have great VSOC support, and so we adopted Rust. We also needed to debug issues occasionally in production, and we needed to invest in some custom tooling which would make this easier without sacrificing the enclave security model. And then we also needed to begin scaling up our enclaves. So as we began to see more traffic, we needed to tune the performance of the processes running the enclave. But overall, our use of enclaves has proved to be a big success, both from a product perspective. We have peace of mind knowing that only one small service is able to access the most sensitive data. And then additionally, from a business perspective, our customers also found it reassuring and felt that we were responsibly using their keys. And so our new product, Evervault Enclaves, is effectively packaging up what we've learned from the last couple of years of running enclaves in production and making it easier for teams to adopt them for existing services. So we have some features which make it easier for the initial adoption phase. These are an easier build process, features that support the lift and shift of existing services, clients that support attestation out of the box, and then manage deployment pipelines. So digging into these individually, our build process is quite simple. We take a user's Docker file, we inject in some custom Evervault directives which install our runtime and abstract away the enclave environment, and we produce an EIF artifact, an enclave image file artifact, directly on the customer's machine. So we have no involvement in the build process, which means our customers have full confidence in the attestation measures they produce. Our CLI also makes best effort at reproducible builds, and this is largely built on the work done by Akihiro Suda as of build kit version 12. And then we have support for pinning signing certificates. Our customers generally want to lock down their production environment, and they want to scope the access to their private key used to sign the images. So we support locking down their deployments and rejecting any attempted deployments which use any other key pair. And then our runtime is also implemented in Rust, as discussed earlier. And we use Rust's compile time feature flags to compile away features that customers don't need. So if a customer doesn't need, say, network egress, they will install a version of the binary which does not even include the support for egress, which is then inherently present in their attestation measurements. And then to make lift and shift of existing services easier, we provide some config options that are consistent with existing on-demand compute platforms, like environment variables and secrets that are loaded in as the process starts. A nice feature of our secrets is that the secrets are encrypted on the user's machine using their key pair. And we'll talk a little bit more about that later on. And then the in-enclave runtime abstracts away the enclave environment. It manages the enclave host bridge over vSock, creates a loopback interface so our customers can just listen to a TCP socket as normal, and also handles things like TLS provisioning, termination, exposes attestation documents, and then also supports some allow listed network egress. And then we also have clients that have attestation built in. So we maintain a Rust library which validates attestation documents, and then we expose FFI bindings to 5 different languages, which then allow our SDKs to support attestation out of the box. So our 5 SDKs, Node, Python, Go, Android, and iOS, can all attest customer connections to their enclaves. We also have an additional feature that allows customers to sync their attestation measures from a trusted provider. So that may be pulling down the latest measures produced by their CI pipeline, or they can even pull them from Evervault as an API. And finally, we manage the deployments of their enclaves. So the customer builds the image, but they just provide it to us for deployment. So they have full confidence in the attestation measures, but this introduces some interesting caveats for how we consider the enclave in production. We manage the instance provisioning, configuration, and routing, scaling. We apply security patches, and then we also have some nice features such as notifying when the enclave signing cert is expiring, so a customer can proactively roll out new PCORs to their clients. And so the trust model for our enclaves product, when we're managing deployments, it becomes quite an interesting trust model to consider. From our perspective, we only want to trust the process that we manage and that we've built, which is our host process, what we call the control plane. From our customer's perspective, though, they just want to trust their own source code that runs in the enclave. They've built the image on their machine, and they use those attestation measures to build confidence that that's what they're speaking to, but they don't want Evervault to be part of the equation. And so they use our CLI to build their image. The image that's built includes our runtime, but both of these projects are open source, so our customers can audit them and build confidence that there's nothing untoward going on. And we only involve ourselves with the orchestration of their enclave, not the build step. So we can't make any assumptions about what actually runs within the enclave. And so from our perspective, we wrap their image in our control plane, our host process, and we launch the host process with the unique identifier for their enclave, as well as some internal credentials like an MTLS client certificate, which we'll discuss later. So we don't know if the image running in the enclave has a legitimate Evervault runtime within it. And so from that perspective, we have to consider the enclave to be an untrusted entity within our cloud environment. And so we've developed a protocol for startup that allows us to use attestation to authorize enclaves to access sensitive material. So we're going to walk through that now. So as the enclave boots its process, it sends a message to the control plane process running on the host to begin the startup handshake. When the control plane process receives this message, it sends a request over an MTLS connection to the provisioner, and that includes the enclave UUID. The provisioner is just a pretty simple REST API that has access to a read replica of our deployments database for enclaves. So the provisioner receives that MTLS connection. It knows that it's speaking to the host process and can be trusted. And so it signs a token, effectively just a JWT, that includes the UUID of the enclave that it was given, plus the IP of the host that sent the initial connection. And this is just a short-lived token. The control plane process and the host then sends this as a response back into the enclave over vSock. So when the enclave receives this token, it then generates a new attestation document, and it provides the token itself as the challenge. So once this is done, the enclave then sends another request to the host. This request initiates a TLS handshake from the host process, the control plane, to the provisioner. This is just standard TLS, it's not MTLS. So the provisioner knows that it has to treat the client connection as somewhat untrusted. So the enclave, once it's established its TLS connection, will send the attestation document that contains the token as a challenge. Once the provisioner receives this attestation document, it's able to decode it, validate it, and then extract the PCORs from it and cross-reference them against our database. Additionally, because it was the original signer of the token, it can validate the signature over the token, which allows us to correlate the trust of the control plane host process with the trust of the enclave and its PCORs. And so what assertions can we make from this? We've effectively verified the integrity of the enclave. So we have a database that stores the PCORs that our customers provide to us at deployment time, which we then know are effectively the PCORs that our customers trust to receive their configuration variables. And by cross-referencing the PCORs from the attestation document against this table, based on the UUID given to us by our trusted process on the host, we have proven that the enclave that we're speaking to is trustworthy. Additionally, by verifying the IP within the token, the IP of the subsequent TLS connection that comes from within the enclave, we're able to trust that the host process has shared the token with the expected enclave, and that the connection is coming from within the enclave that we expect it to. And so once all these tests pass, we know that we can trust the enclave. And so once we trust the enclave, we provide it back its secrets and environment variables, which are required for it to boot up and spawn the user's process. So again, those secrets, as mentioned earlier, were encrypted on the user's own machine, and so those will still be encrypted, and the enclave will use a pretty similar attestation handshake to get a new token after this to speak to a different internal service, the encryption engine also mentioned earlier, to decrypt those secrets so it can boot. And so what can we take away from this? By using attestation within the boot up flow for our enclaves, we've introduced the challenge of image integrity beyond instance identity. So typically in instances, boot up flow or its access within a system is allocated based on, say, a role it's given based on its identity, whereas by incorporating attestation into this handshake, we're able to verify the integrity of the image being deployed. Thank you.